I am a protector, exploring the expanses of space to keep our planet safe, and all the species that call it home. I am a healer, giving doctors the vision to create amazing new cures. And using the heart's own magnetic field to diagnose itself. I am a guardian, searching a mountain of data to keep us safe when we travel. And a sea of people to find a lost child. I am a helper, powering autonomous machines that simplify our lives. Capture our greatest adventures. And make us whole again. I am a visionary, enabling taxis that don't need steering wheels, and those that don't need roads. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
Hi, welcome to GTC, welcome to Santa Clara. GTC is the GPU Computing Developers Conference. We do it for you, for all of you whose work are simply impossible without a supercharged computer. Thousands of NVIDIA employees and our partners worked incredibly hard to pull GTC together for you. Let's give them a round of applause. Thank you, guys. I love you guys. Thank you. We have so much to talk about today. We have a lot of new products to show you. We're going to talk about amazing graphics. We're going to talk about amazing science, amazing AI, and amazing robots. We have so much to cover, so let's get going. Computer graphics is the driving force of the GPU. It is computationally insatiable. Recreating virtual reality is one of the most daunting computing tasks we know. And yet, on the other hand, it is an enormous industry. We want to visualize information, visualize experiences in all kinds of markets. As a result, the technology that we bring to bear and the size of the market combines into a gigantic R&D budget. It is the driving force of GPUs. Since 1979, when Turner Whitted wrote the paper on recursive ray tracing, in 1986, when Jim Kajia described the rendering equation, the computer graphics industry and computer scientists all over the world have been pursuing this holy grail, this dream of recreating photorealistic images. This is the way film is done. They trace rays through a scene as it strikes a surface, calculates the absorption, the reflection, the refraction, the luminescence, accumulates light from all the different sources and reflections and calculates the reflectance functions based on the materials that it strikes, accumulates all of that information, and generates a photorealistic image. Well, this is the way the film industry does it. And it takes thousands and thousands of CPUs and thousands of servers in order to calculate and compute each one of these frames. One CPU would take hours to compute one frame. And a movie has, as you know, hundreds of thousands of frames before they could create the final film. Well, when you look at this image, it is utterly beautiful. It's just super, super hard to produce. Well, the computer graphics engineers and architects at NVIDIA isn't sitting still either. This is what modern computer graphics looks like. This is what a video game would look like. And in fact, it looks pretty amazing. The difference here is what I showed you earlier was generated one frame every many hours versus what's going on here with real-time rasterized computer graphics with programmable shading that we invented some 15 years ago, produces these images at 4K resolution at 60 frames per second. From one frame in many hours to 60 frames per second, that fundamental difference has been a gap we've been trying to close for literally 4 decades. Literally 4 decades. And in fact, it is incredibly hard. We look at this image today, and I can't tell you how proud I am. I mean, this is modern computer graphics. Look how incredible it looks. And yet, there are so many places we like to improve. For example, we use all kinds of special techniques to trick your eyes to see reflections, to see shadows. Ambient occlusion is where light accumulates on a surface, and because different surfaces are further away or occluded from the ambient light, it's darker. It's not a shadow, it just simply wasn't illuminated. Ambient occlusion. We use all kinds of tricks with our Z-buffer depth tricks to calculate in our programmable shaders to figure out which one of those pixels ought to be darker than the others. We use all kinds of tricks. Game developers will even render the scene completely in advance. And for all of the places where there are static lights, we will pre-bake the light. It's called light baking. But as a result, as you can see, so long as things don't move very much, the lighting conditions are relatively well reproduced. And it's quite beautiful. This is what ray-traced image would look like with global illumination. Notice those little details that bring a scene to life. The little details that bring a scene to life. So ray-traced global illumination, where light is simply emitted from everything that has a light source or is reflected. Diffused interreflection, where even objects that are matte in color could actually emit light as light reflects off of it. Global illumination. We use screen space reflection and environment maps. We render the environment and we create a cube map, which is then used as a texture in combination with our shader programs to recreate reflections. Or we could do it using ray tracing. Incredibly computationally intensive, but much, much more beautiful. We could do refractions as light travels through that glass. But as you guys know, refractions are hard to do, especially with the glass, because the glass has curved surfaces, and every time when you guys look at sun shining through a swimming pool, the curved surfaces accumulate a light volume that causes the refraction to look with these spines of shapes of light we call caustics. Notice it's very, very hard to do that here. In fact, it's not even visible here. We use all kinds of techniques to create the translucency of glass. And this is what it would look like if it was ray traced. It looks like crystal. And notice the beautiful caustics that are here. The beautiful caustics. Imagine if the light was moving. There are objects that absorb light. They absorb light, but they bounce inside and they re-emit the light. Subsurface scattering. Jade does that. Gummy bears do that. Car paint does that. Your skin does that. And that's why we don't look like a brown blob. That's why we look alive. Light goes through, picks up a little bit of shades of red, bounces around in your subdermis, and then reflects out. Makes you look alive. Subsurface scattering. We use all kinds of techniques to fake it today. Using ray tracing, the gummy bear looks like you can almost pick it up and eat it. Incredible. Incredible. And then here, we didn't show it here, but this gummy bear is actually being lit with the light from the caustics. All of those computationally intensive problems, the effects of light as it travels through your room, the environment, is so hard to compute. It is so hard to compute. And that's the reason why ray tracing has been so popular in film. And it is the holy grail, the dream for computer scientists for the last 40 years. It's incredible to see this when you look at it in motion. And so here's an example of it in motion. Let's take a look at this.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector. If you ask me, who's ever in charge of this place should be transferred to Hoth. What? What? You think she heard us? Yeah, I think she heard us. At least we blend in for once.
Wow. Well, first of all, what you were looking at earlier was not a scene from the last Star Wars movie. In fact, it wasn't a scene in a movie at all. What you just saw was completely rendered in real time. Now let's show it to you. Okay, who's driving this morning? Steve, is that you?
Yep, we're here.
Okay, all right, this is
Got
Dr. Stephen Parker. He's been working on ray tracing his entire career. Since joining NVIDIA 10 years ago, this has been the undertaking, this has been the endeavor of literally so many people in research, in software, in architecture, in hardware. Everybody's working together to make this possible. Now here, what he's going to show us now are some of the special effects that you can imagine, that you can do if you had ray tracing.
We've been working with Epic Games and ILM X Labs on a special project and are showing a prototype of RTX integrated into Unreal Engine 4 through Microsoft's DXR. In this case, we're showing area light shadows, which are quite important for cinematic visual effects. The tricky part is to get the contact hardening or the sharpening of the shadow near the base of the stormtroopers where they touch the ground. It's an important visual cue that helps us understand that those people are standing on the ground. And then we can also see them in a more complicated environment.
Now, Steve, the thing to say is when you say area lights is where light is being emitted from an area instead of a spot. Spotlights are relatively easy to do. Area lights are really hard to do. And the reason for that is it's essentially a whole bunch of spotlights. And so the way that the shadow, the way that reflection works and the way that shadow works, shadows are so soft. And notice that there's so many different essentially the accumulation of a whole lot of shadows, and that's why they're so soft shadows.
Exactly. And in cinematics, it's important to control the shape and scale of the light so that you can control the shadows so that they fall where the producer would like them to fall. So,
that's incredible. Well, let's take a look at another scene.
Let's see
so
something
this is
shiny.
shadows and lighting. Now this is reflection.
So another thing that ray tracing is really good at is reflections. We can see them here in an environment such as the elevator that we saw in the clip. You can see the reflections on the stormtroopers as well as them reflecting each other. But to really show them off, we need to bring in something even more shiny. And so
now
here,
look at this. This is reflections on reflections. Check out Captain Phasma's gun reflecting on Phasma's chest right there. You see that? Reflections of reflections.
So all those things have to be shaded multiple times, shading the primary surfaces as well as the reflections, and that's one of the things that makes it really difficult.
And these rays are bouncing all over this environment. These rays, every single one of those rays are bouncing off the environment, and every time it strikes a surface, it has to figure out, do I reflect, do I refract, am I absorbed, and how much is it absorbed? Where does other rays come from that I need to accumulate? And then it bounces off, and it goes to another place, and it strikes another surface. And then it strikes all these different surfaces. This light is bouncing all over the place as it strikes these surfaces, figures out what the rendering equation is at that moment as it strikes that surface, accumulates it for the entire scene with all of these billions and billions of rays. This is how this is recreated. Now, of course, doing so would just take an enormous number of computers. And that's why film studios have supercomputers. That's why Pixar has supercomputers. That's why Industrial Light and Magic has supercomputers. And they use these supercomputers to calculate these rays one at a time as it bounces and strikes these surfaces and creates this image. And the more reflections, the more refractions, the more ways that the ray can bounce before it's absorbed completely, the more reflections and refractions, the harder it is. There are so many little visual cues. Stephen Parker, NVIDIA ray tracing team. What an amazing achievement. Ladies and gentlemen, everything that you're seeing here is completely in real time. Now, this complete demo, yep, there you go. It's completely in real time, and it's running on one DGX station. Instead of a supercomputer rendering these scenes one frame every 10 hours, this is now running on one DGX computer with 4 voltas in real time. This is what we can do now. $68,000 computer versus a supercomputer. That's great. Thank you, guys. So, ladies and gentlemen, we're announcing the NVIDIA RTX technology. This has been 10 years in the making. You have seen us demonstrate pieces of it over time. But today, this is a very, very big deal. This is a very big deal because for the very first time, and by the way, I want to thank the team at LMX Labs and Epic and all of the engineers at NVIDIA that worked on this. This piece of work, the Star Wars rendering in real time, is really one of the first times that ray tracing has ever been done it is the first time that ray tracing has been done at this level in real time. So thank you very much, guys. Super proud of you guys. After 10 years, what makes this special is for the very first time, we can bring real-time ray tracing to the market. People can actually use it. The technology has been encapsulated into multiple layers, from our GPU architecture to the algorithms that makes it possible for us to do this. You are also seeing deep learning in action. Without deep learning, it would be impossible to have traced all of those rays. We use deep learning to essentially, whereas deep learning has been used in the past for super resolution, we're using them for super rays, predicting rays, so that we could fill in the spots that we know what the right answer is going to be using artificial intelligence. And so NVIDIA Volta GPU, the RTX technology, the solvers, the architectures, the libraries, has now been integrated into three of the most important rendering APIs. One, the NVIDIA optics. Two, Microsoft's DX12 extension called DX Ray Tracing DXR. The work that we did with them is fantastic. And then now it's also going to be available in OpenGL Vulkan. We also are announcing today the world's largest GPU. The world's largest GPU. It's called the Quadro GV100. It is so large, we decided to paint it gold. Ladies and gentlemen, this is the Quadro GV100, the world's first workstation GPU based on the Volta architecture. It also is the first one that has a brand new interconnect between GPUs called NVLink 2, super high-speed interconnect between the two between two GPUs that basically extends the programming model, the memory model, out of our GPU into the other GPU, which means all of the memory reads and writes and all the atomics work exactly the same. Software doesn't have to change. The two GPUs connected through this new interconnect called NVLink is essentially one giant GPU. So these two GPUs working together, two GV100s, will become a revolutionary new workstation. It's going to be available from HP, Dell, and Lenovo. I think the announcement goes out today. It'll be available relatively soon. These two GPUs combined has 10,000 cores, 10,000 CUDA cores, 236 teraflops of tensor cores, all used to revolutionize modern computer graphics. The largest frame buffer in the world, 32 gigabytes of HBM2 per GPU, two of them together working completely unified inside an application of 64 gigabyte frame buffer HBM2. Ladies and gentlemen, the Quadro GV100 with the NVIDIA RTX technology. Thank you, Paul. Creators and designers are going to love this. It is amazing how many frames are rendered each year. There are 400 games being made every single year. This is one of the largest industries in the world. And all of those beautiful lightings that you see is made possible by the technology, the technique that I described earlier called light baking. Basically using ray tracing to render the entire game in advance. And wherever there are static lights, bake it. Put it right into a light map. As a result, you get these wonderful crevices and shadows, and all of these details come out, and the whole world comes to life. The film industry uses this technology. Mowgli and Bagheera wouldn't be possible if it wasn't because of rendering technology. 500 movies made each year. Every single frame has been rendered multiple times during design, and then finally has to be done in final film. 10 hours on the highest performance GPU per frame. Just imagine how many CPUs per frame, how many CPUs are in those render farms. Product design. When you see advertisements and you see these commercials and these cars are driving around and they're being launched all over the world at the same time, the cars don't exist. They're all completely created using photorealistic rendering. Architecture design. There are no square buildings anymore. All the buildings in the world are beautiful, gigantic products. And the only way to imagine what it looks like inside, feels like inside, is to render it photorealistically. Architecture. We estimate 1 billion frames are rendered each year. With the NVIDIA RTX technology and the Quadro GV100, I believe the number of frames that will be rendered will jump by a factor of 10, just so that you can iterate and try things before you get it done. You also get it done faster, but most importantly, you'll save money. As you know, everybody knows now, this is like common sense. The more GPUs you buy, the more money you save. That's right. The more GPUs you buy, the more money you save. This is now common sense. Now, let me illustrate it to you. This is what a render farm would look like. Look at this thing. It's incredible. 280 dual CPU servers. It consumes 168,000 watts. That's like 168 families and their homes being used to render images. This is before, this is after. This is with the NVIDIA RTX technology, Quadro GV100. Look at this. 14 quad GPU servers, 24,000 watts. And you save millions of dollars. You save millions of dollars. This is what it looks like before. Probably a few $1 million. Call it 3, 4, 5. And this is what it looks like now. A few $100,000. Save millions of dollars. Come to GTC, learn how to save millions of dollars. Well, the industry is just so excited. We're so grateful for the adoption and the engagement and all the work that we're doing with the industry. From tools makers, Adobe, Autodesk, Dassault, engine makers, Epic, Unity, film studios, Pixar, Industrial Light, Magic, they've all come out to adopt this technology. The NVIDIA RTX technology will completely revolutionize the way they do work. They could finally do ray tracing in real time. Try more frames, create more beautiful shots, deliver to the customer faster and on time, and more importantly, most importantly, save millions of dollars in the process. Incredible support from the industry. Gaming, design, film, architecture. This technology is the single most important advance in computer graphics in the last 15 years. And I say 15 years because programmable shaders that we invented has basically defined modern computer graphics. I believe NVIDIA RTX is going to define the future of computer graphics. This is a very, very big deal. It's a very big market. Super, super proud of all the engineers that worked on it. Thanks a lot, guys. Good job. One of the best decisions we ever made was 15 years ago when we decided that a GPU, which was a graphics accelerator at the beginning, would become more and more general purpose. We wanted to become more and more general purpose because we felt that in order to create virtual reality, we had to simulate reality. We had to simulate light. We had to simulate physics. And that simulation has so many different algorithms, from particle physics and fluid dynamics, and of course, what you just saw earlier, ray tracing. The simulation of the physical world requires a general purpose supercomputing architecture. My kids told me this morning, Spencer and Madison told me this morning that this is our 10th year anniversary. The first year was called Envision. Since then, it was called GTC. This is our 10th year anniversary. We started GTC because we wanted to promote and to enable the industry to create applications on our GPUs. Because our GPUs are going to become more and more flexible. Over the years, we've advanced the architecture because accelerators tend to be very, very good at one thing. You accelerate one thing. Over the years, we've expanded the flexibility of our GPUs without sacrificing that one thing, which is accelerating computer graphics to its extreme, or accelerating whatever application. And of course, one of the applications you guys know very well about is our work on deep learning. Accelerating those applications to the speed of light, creating tools, creating systems, creating interconnect, evangelizing the programming model, all of you creating software and solvers on top of it, step by step by step, over the course of 10 years, and all of a sudden, one day, boom, the tipping point happened. It became a common sense computer architecture. It became a computer architecture that is available literally everywhere. And it couldn't have come at a better time and a more important time. At a time when all of these new applications are starting to show up, where AI software is writing software, but it needs a supercomputer to do it. Where supercomputing is now the fundamental pillar of science, where people are starting to think about how do we create artificial intelligence autonomous machines that collaborate with us, that augment us. The timing couldn't be more perfect. Well, we're at the tipping point, and the number of people who are jumping on top of GPU computing is really growing and growing at an exponential rate. We're almost up to 1 million GPU developers, up 10 times in the last 5 years. The number of attendees of GTC, we are packed all the way to the end. We're packed all the way to the end, and we've got overflow, and Santa Clara is at its limit. Silicon Valley is at its limits. It has grown 4x in the 5 years. GTC is now a global event. The number of CUDA downloads has increased 5x in 5 years, but here's the amazing thing. 8 million downloads of CUDA, almost half of it was last year. 8 million downloads of CUDA, almost half of it was done last year. And remember, we started downloading it 10 years ago. The number of GPU flops in the top 50 supercomputers in the world has grown to 370 petaflops. We just announced our nation's 2 fastest supercomputers, Summit and Sierra, both GPU accelerated, each one of them about 100 petaflops. The fastest supercomputer in the United States was 20 petaflops, the Oak Ridge National Labs Titan. 370 petaflops is equivalent to three of the world's fastest supercomputers. 370 petaflops, an incredible amount. 15 times in 5 years. 15 times in 5 years. So clearly the adoption of GPU computing is growing, and it's growing at quite a fast rate. And we need larger computers. Even then, we need larger computers. The world needs larger computers because there's serious work to be done. There's serious groundbreaking science to be done. And there's so many examples of them. Whether it's reinventing the way we store energy, trying to understand the Earth core to predict future disasters, understanding and simulating weather, or just understanding how HIV viruses work. Each one of these simulations take days on the world's largest supercomputers. In the case of the work that is done at Caltech, 7 days on a Titan, 2 weeks on a Titan, 840 days, almost 3 years on the PIZ-DANT supercomputer. And of course, Blue Water, almost 2 weeks to simulate the HIV virus. Well, what's going to happen here is this. We're going to go build an exascale computer, and all of these simulation times will be compressed down to 1 day. But what's going to happen at the same time is that we're going to increase the simulation model by a factor of 100, and then we're back to 3 months. And then we'll go figure out a way to build a 10 exaflops computer, and we'll be able to reduce that simulation time. And then, of course, the size of science we'll be able to do will grow again. Science needs supercharged computers, and that's the reason why we're building supercharged computers. If you take a look at the last 5 years, there's no question now GPU-accelerated computing is the right answer. On the left, on this side, which is that? On the right is Fermi. This is our first GPU that you probably got to know about us, where the GPU computing universe learned about NVIDIA. This is the GPU server circa 2013. This is the Volta server 5 years later, circa 2018. The amazing thing is running the simulations of these molecular dynamics codes, and there's so many of them, trying to simulate the human biology. The speed up that we created in the last 5 years is 25 times. Well, Moore's Law is 10 times in 5 years. Moore's Law, the miracle of laws, the law that has enabled just about every single industry and progress of science and the progress of society, was compounded over time 10x every 5 years. 10x every 5 years. Our GPUs have accelerated these molecular dynamic simulations 25x in the last 5 years. There's a new law going on. It's a supercharged law. There's a new law going on. And I think this is the future of computing. Well, the question is, how did that happen? Well, the way that it happened, of course, is it starts out with a highly specialized parallel processor. A highly specialized parallel processor we call the CUDA GPU. And of course, it is the largest and most complex semiconductor the world makes. But it's much, much more than that. The interconnect of these processors, the memory system of these processors, the way that it's architected into systems, all of the software on top of it. And I'm just showing you some of the stacks. Look at this. From cuBLAS, linear algebra, FFTs, random numbers, sparse linear algebra, the software stack in 2013 was 5.0. Amber 12.12, version 12. This is Amber 16. 9.0 across the board. Basically, we're continuously updating and continuously refining these algorithms and these solvers. We could design new architectures every single year. That's how we got from Kepler to Maxwell to Pascal to Volta. On top of it, we create new interconnects, NVLink. On top of that, we embrace new memory technologies and drive it to the speed of light. On top of that, we have new solvers and algorithms. On top of that, we work with system makers to create new systems. And on top of that, we work with all of the application developers to refactor, to optimize their software so that the entire algorithm could be highly accelerated. Now, the benefit to science is incredible. This is what a supercomputing rack looks like. It's much, much more densely populated because most supercomputers deliver a lot more power per rack. 20, 30,000 watts per rack. This is 600 dual CPU servers, 360,000 watts. And this is what it looks like if it was GPU accelerated. That's right. Work with me here. The more you buy, the more you save. That's right, work with me here. The more you buy, the more you save. This is not a complicated talk. Guys, this is not a complicated talk. First of all, I want to congratulate, speaking of talks, I want to congratulate John Hennessy and Dave Patterson for the recognition of the work that they've done, the Turing Awards. Hey guys, isn't it amazing? John, you're my hero. Speaking of talks, the guy gives just the most amazing computer architecture talks. This is not like one of them. This is much easier. There are only 2 messages I want to deliver today. One of them is, the more you buy, the more you save. Okay, all right, there'll be a quiz at the end. There's a second quiz coming up. NVIDIA Tesla V100, big savings for HPC. One of the most important and one of the applications that I love the most of all of the work we do in HPC is the work that we do in revolutionizing modern medical imaging. Well, it turns out that early detection is the most powerful weapon against disease. The sooner you detect, the better. This is true for autonomous machines of all kinds. The sooner you detect, the better you detect, the better. Well, whether it's CT, computer tomography, magnetic resonance, ultrasound, mammography, which is low-dose X-rays, the positron emission, PET, each one of these modalities of medical imaging has been revolutionized recently using computational approaches. In fact, CUDA is embraced, and our GPUs are embraced throughout the medical imaging world for this very reason. Because it could take these sensors, these weak sensor information, do image processing on it, reconstruct a 3-dimensional image, visualize it, segment it, detect things using deep learning. All of these techniques have now come together in medical imaging. On the left is a 15-year-old ultrasound image. In fact, it hasn't changed very much over the years. Most ultrasounds that you see in hospitals still look like that. On the right is a brand new medical imaging equipment from Philips Epic. It's unbelievable It's unbelievable. It could do 3D reconstruction. It could visualize. It's as if there's a virtual light inside the womb. Look how beautiful it is. It does 3D segmentation, so it detects the baby and lifts it out of all the noise, and then it does beautiful rendering. And here you could tell they're using some amount of subsurface scattering so that the baby looks like there's the tone of flesh. Okay? Modern ultrasound. Well, this technology is used everywhere, as I mentioned. It's used in CT, MRIs, in PETs, in mammo, in ultrasound. And in addition to that, modern advances in deep learning and artificial intelligence is about to revolutionize the entire industry. We can now reconstruct images better than we could ever before. We could identify and segment brain tumor better than ever before. And we can visualize the images in a way that reveals a lot more insight using cinematic rendering than we ever could before. The entire stack of NVIDIA, from the GPU containers, the virtualized GPUs, CUDA, cuDNN, RTX, OpenGL, all of the solvers and all the libraries integrated into these imaging applications. That entire stack is identical to everything that I've talked to you about. It's identical to everything I've already talked about. Well, the unfortunate thing is this. There's some 3, 4, 5 million medical instruments that are installed all over hospitals all over the world. So let's call it 3 million instruments. 100,000 new ones are being sold each year, which basically says it's going to take about 30 years before we can replace the installed base. And so the question is, how do we solve this problem? We can't wait for 30 years for doctors to be able to have early detection and have this powerful technology in their hands. And so the question is, can we take advantage of the same basic techniques that we've now seen in modern computing, where you have connected devices connected to data centers, and those data centers essentially have supercomputers that are virtualized. We have an initiative, a project in our company we called Project Clara. Clara, in short, is a medical imaging supercomputer. But what it is a data center, virtualized, remoted, multimodality, multi-user computational medical instrument. Well, that is such a long description of what it is, we decided to call it's a medical imaging supercomputer. You could put it in the data center, you can put it in the cloud, and because of the technology we've already talked to you about, it's possible for us to actually virtually upgrade every single medical instrument. Let me show it to you. Fausto.
Hey.
Fausto, hey, man.
So what we are seeing here is a...
Wait.
Oh, sorry.
Yeah, LUA, buddy. Forget it. Inside joke. I want to prepare his language so that you understand it. No. This is one of our scientists in our company, and this is his field of expertise. This is where he dedicates his life. Dr. Fausto.
Dr. Jensen.
That's right. Every time I call him doctor, he calls me doctor. And another inside joke. Hey, with your friends in the company, you got a lot of inside jokes. And so Dr. Fausto has been working on medical imaging for some time. And so what he's about to show you is something that's really amazing. Go ahead, tell us.
So, sure. So what you are seeing here is a beating human heart, and this is an echocardiogram. Actually, we are seeing the left ventricle of the heart, which is pumping blood. And basically, this is the type of image that a doctor would look at when he diagnoses your heart functionality. And yeah, so this is 2D, but our body, of course, is 3D. So there is more information from the scan that we can acquire. So when we switch to 3D, we see a more complete picture like this.
And so this basically is a scan. It's an traditional ultrasound scan coming off of a 15-year-old instrument that we then take into this computational medical imaging supercomputer, this MIS, and this is what comes out of it. Does that make sense? Okay, you take this ultrasound machine that's sitting in a hospital, it's already on the network anyways, you stream the ultrasound information into your data center, and your data center running this stack on top of a GPU server creates this miracle on the right. And now it's volumetric. Keep going.
Yes.
That's nothing. Wait.
Okay, so,
so excited.
At this point, we see that we barely see basically the chambers here, and we can analyze more of the motion of the left ventricle by using deep learning. And we resort to use a state-of-the-art deep learning method. It's a fully convolutional neural network in 3D called VNet. We revisited it. We used the unprecedented resolution of 256 cubic voxel, which is 16 million values per scan, per frame. And we have asked deep learning to interpret it for us. And now we can see the chambers moving across the cardiac cycle, the left ventricle moving across the cardiac cycle, and segmented very well.
Now, just think, you got to realize what's happening. There's an artificial intelligence network here that is running on the original black and white gray scan that you saw. And from that scan, from that ultrasound scan, it inferred what this left ventricle, where the left ventricle is. It segmented it out. It segmented it out in motion, and it segmented it out in 3D. Guys, if that's not amazing, that's pretty incredible. That's pretty incredible. Keep fast out. That's amazing work, man. Go.
Of course, there is more even to this story. So now we can get values. We can get very precise explanation of what we are seeing, and markers that tell us how well the heart is functioning. We can get the ejection fraction, the volume of the chamber of end systolic and diastolic moments, and the amount of blood that is ejected with each heartbeat. And we can just augment the view of the doctor in this way, in an almost transparent way, where the 2D view is augmented with the 3D information.
That's cool. Fausto, thank you. Your ejection volume was running about 80%.
At this moment, yes.
You think so? Maybe 99%, everything coming in was going out. That's fantastic. And so here's what we're going to do. We're going to create this server with this stack, this virtualized stack on top, and it's going to be remoted into all of these medical instruments all over the hospital, and then you'll be able to scan using your current installed base of scanners, and then we'll post-process it using AI to infer more information from it. We could also use all kinds of new computational techniques to improve the image and to visualize that image. We call this the medical imaging supercomputer. It's so great. We have partners all over the world working with us, and there's, this is an area that we've been working with and working on for quite some time. And so NVIDIA's new project, Clara, this brand new platform of ours, we're getting a lot of advice and developing and working with startups and research hospitals and healthcare providers in all the different modalities. Okay? Ladies and gentlemen, Clara.